Okay, here's what we're going to do. We're going to look at a few problems that are very closely related to different ways you can use integration. And we're just going to start with just some stuff that I've found here that may help. So if I have a velocity equation that looks like this, v of t equals 6 cosine squared t, sine t, and we're looking at that velocity from 0 to 2 pi. If we want to know how far the distance that we've gone would be, we need to find the position. And so if you integrate velocity, if you integrate the velocity function, you'll get the position function, which is often referred to as s. So on this particular problem, if we're given if we want to know the total distance traveled, okay, this would give us net distance here. If I want to find total distance, then I would integrate the absolute value of velocity. That'll give us a position function, but in this case, it'll give us total distance covered. There can be a big difference between total distance and net distance. You might move 3 feet, but you might travel in a ginormous circle to do it. So we wouldn't know that unless we did total distance. So if I ask you to find the total distance covered, the question is find the total distance. Once my pinwheel goes away here, let's get rid of that guy. If I say find total distance, then what we want to do is look at that second integration setup. The equation they've given us is 6 cosine t squared sine t. And the beautiful thing is, for the students that I teach, we've already integrated. So I don't mind if you use some technology to help you out with this. We're going to integrate from 0 to 2 pi. And we're going to put in 6 cosine squared t sine t. Go ahead and use your calculators. It's okay. It'll give you an approximation. And make sure that you go at least 3 decimal places with that. But in this particular case, it works out perfect to be 8 units of space. We weren't told how fast we were going. Let's see, what are we? We're told meters per second. It tells us this is going to be meters per second. So when we integrate that, we lose the seconds, and we go 8 meters. So there you go. There's a velocity to position function, and you use integration to find that. Okay, let's look at another problem now, maybe one that involves acceleration. So if we're told that we have an acceleration function that looks like this, acceleration is 1.5 plus 2 squared roots of t, and that's in miles per hour. And I want to, and this happens for 16 seconds. Acceleration lasts for 16 seconds. Okay. What is the velocity after that 16 seconds? So if we accelerate continuously for 16 seconds, what's velocity equal? Well, remember that if we want velocity, we integrate acceleration. Okay. In this case, to give us an acceleration problem, they give us the function for that. So we can integrate that. We're also told that for 16 seconds, that is what our integration is. So if we're looking for this velocity, then all we need to do is integrate from 0 to 16, the acceleration function. If you're in my class and one of my students, we've already tested over integration. And unless we need to do something where we don't have a definite integral, you're allowed to use your calculator to help you sort this guy out. So just punch him in, and you end up with 109.3. And if we're talking about velocity, we're talking about a distance and a rate. So this would actually be miles per hour. Because usually, typically, acceleration is like meters per second per second. So like this acceleration would be in miles per hour per second. And I forgot to write that down. for 16 seconds. So when we integrate that, we lose that per second part, and we're just left with miles per hour. So integrate acceleration, get velocity. Integrate velocity, get position. And if we wanted to know how far we had traveled over that 16 seconds, we could integrate again and do that. For this problem, we want to find the area of the region bounded by the curves y equals 7x minus x squared and the curve y equals 12. Okay. And to do this, basically, we need to know where we're at and what's going on. So graph this on your calculator. And when you do, you'll notice that you get a parabola that opens down. Something like this. And you get a line y equals 12. Something like this. Okay. What we're really super interested in are these points right here. And we want to find the area that's in here. Okay. So that's the goal. And how do you do that? You very simply integrate. Whoop, we don't want to use that one anymore. We want to integrate from A to B. We want to integrate from A to B, the top function minus the bottom function. Okay? Top minus bottom. And when you do that, what will be left will be that little shaded in highlighted area. So all we need to do is determine what A and B are. There's a variety of ways to do this. You could set the two equations equal. You could graph them and find where they intersect. You could use a calculator. You could guess and check, although that's pretty risky. So that, if we just set these two guys equal to each other, I like to solve out where my x squared is positive. So I'm going to move x squared and 7x over. You can either use the quadratic formula or recognize that this will factor. That is a nasty 0. And this is going to end up being x and x and minus 3 minus 4. So set each piece equal to 0. And you're going to see that we're going to integrate from 3 to 4. The top equation, which happens to be my parabola, so 7x minus x squared, minus the bottom equation, which happens to be 12. And that's the setup for this particular problem. This one is actually really easy to integrate by hand. But if you're one of my kids, you don't have to do that. You can use your calculator. Depending on your professor or teacher, please follow their instructions. My students have already demonstrated to me they know how to integrate, so we go ahead and move into the actual technology part of this, which will also help in the long run. So when you punch this into your calculator, that will give you this area right in here. Okay, that's all there is to it. If you integrate it, then you should also be able to get to the same thing. And let me see if I can find the right color. But ultimately, this is going to take you to 1/6, I think. Yep, takes you to 1/6. So there you go, integrating and just finding area between two curves. Okay, this time we want to find the area in the first quadrant, bounded by a couple different functions. So I'm going to go ahead and set up a first quadrant here. And we're going to be bounded by the line y equals x over 8. The line x equals 3. The line y equals 1 over x squared. So what we've got then is a situation where we have x over 8 does this. The line 1 over x squared does something like this. And the line x equals 3 does something like this. These are approximations, okay? And approximations are okay. What we're trying to find is this area right in here. We want to find this area right here. Okay. So how do we do that? Well, we do that by subtracting the area from A to B. We go from A to B and we go our top function minus our bottom function. Top minus bottom. The problem is on this particular one, that shaded region, it changes which function is on top, and it changes right here. So what we have to do is figure out at what value of x this occurs, because we're going to have one integral here and a second integral over here to represent the top and bottom equation. And in this case, the bottom equation on both is going to be that line y equals 0. So we're basically integrating one function for one function for two, and we're going to add those two together. The easiest way to do this is to take x over 8 and set x over 8 equal to x1 over, x squared. Cross multiply. That gets us x cubed equals 8. Take the cube root of both sides, and x equals 2. So this is the point 2 right here. So we've got 0 to 2, 2 to 3. The integrals then that we're interested in will be the integral from 0 to 2 of the top equation, which in this case is just x over 8 dx. And you can integrate that by hand. My kids, you can use your calculators. But whatever your professor tells you or your teacher is the way you need to do it. X over 8 does integrate pretty nice. So, it's not too horrible. 1 over x squared is the next one, and he goes from 2 to 3. This guy also can be easily integrated by hand. And again, my kids, you can use your calculator. So what you're doing is you're adding the first area with the second area to get the total area. The reason we change is because one function's on top and then another function is. And to find the area that's enclosed, we need that top function minus the bottom. So no matter how you do it, once you punch this in, you should get something like 5/12. Or if you had a decimal, 1.467. 4167. It would help if I could read my notes. So there you go. That's finding the area. But now we've got to break that area up into two pieces. And this can happen. Sometimes when we have a problem like this, it's easier to integrate with respect to y. Although this particular problem, I don't know if that's the case or not. But it is something to keep in mind. Okay, now we want to find the volume. Not just area now, but volume. And if we're going to find the volume of something, we need to remember one thing, that volume is equal to the integral from something to something. We'll try and determine what? Of the area of the cross section. So if you integrate area, you get volume, all right? So if I tell you that y equals 4 cosecant x, and that y equals 0, and that x equals pi over 4, and x equals 3 pi over 4, what I'm giving you is the setup for your problem, okay? And graph this on your calculator to get a good look at it. This can be a little bit complicated trying to put all this together. And when you graph it on your calculator, you get this guy right here where you have a cosecant function, which looks like this. And since we're in first quadrant, I don't need a lot of others. We're bound by the, so here's my cosecant, 4 cosecant x. X equals pi over 4, that's this line. So here's pi over 4. 3 pi over 4 is this line. And again, these are rough estimates, but that's okay because we're not going for an exact graph. We just need a good idea to try and determine exactly what our shape is. Y equals 0, that's the x-axis, and we're going to rotate around the x-axis. So what we're really interested in is this area right here. Okay. And as you rotate that, keep in mind what kind of shape you're going to have. And when you rotate something around a fixed point, if I rotate this point right here around the x-axis of fixed point, it's going to sweep out a circle. Okay? Just imagine looking at a Pringles can, and imagine, if you will, every point around the rim of the Pringles can, it's the same distance away from the center of the can. That's the same exact reasoning that we're going to use when we're talking about different curves and areas. It doesn't matter if I'm right here. When I sweep that guy all the way around, it's the same exact distance all the way around. If I pick another point on this curve, it'll be the exact same distance the whole way around the curve. So what have I discovered? I've discovered that my shape, anytime I rotate, any rotation around a point, around a line, around an axis, any rotation is going to give me a disk. A disk is another way to say a circle. And the area of a circle is pi r squared. Okay? So I want to integrate the area of a circle from a to b pi r squared. Here's a, here's b. I am now ready to solve this problem. So I'm going to integrate from pi over 4 to 3 pi over 4. And I'm going to integrate my function of my radius, okay? Because how far away from the x-axis am I at any point between pi over 4 and 3 pi over 4? I'm 4 cosecant theta, 4 cosecant x units away. So what's that going to be? That's going to be pi times my radius squared. Not dt, dx. Okay? That's your setup. That's all there is to it. And then with my kids, we've already integrated. We understand our integration rules. We're going to do this by using our calculator and having that help us. If you are with another teacher, you've got to follow the rules that your teacher gives you. And so you may have to integrate by hand, and that's okay too. Cosecant squared is not a bad thing to integrate. And it'll be easier if you think about your problem this way. We can move the 4 pi in front because it's constant, and any constant can move outside. So we're actually going to integrate this. And you can punch either one of these into your calculator, or you can integrate either one of these. It'll give you the exact same thing. And so when it's all said and done, the volume of the shape swept out by 4 cosecant x is 32 pi, or if you punch it in on your calculator, 100.531. Okay? So there you go. That's a disk. And anytime you rotate, I got to be clear with this. Anytime you rotate around an axis, if you rotate around an axis at either x or y, you're creating a disk shape, a circular shape. Area of a circle is pi r squared. And typically that radius is going to be whatever your function is. All right, let's find another volume rotating around the x-axis. So if we have the equations y equals square root of sine 7x and the equation y equals 1, and we're told that we're going to go from x equals 0 to x equals pi over 14. This tells us exactly what we're going to do. We want to find the volume. So graph it. And I don't really know how the square root of 7x looks on my own. So I used a calculator, and I discovered that square root always has kind of this shape. So I still have that shape, sine 7x. Now, though, we're going up to the line y equals 1. That's going to be this guy right here. And we're going from x equals 0, which is the y-axis, to x equals pi over 14, which is this right here. Okay? Remember the sign. So we're going to be 0 here, pi over 14 there. So the question then is, what is the volume of the shape? And the shape that we're interested in is right here. Now, what's different between this problem and the one I just did is that with this guy, we're going to rotate around the x-axis. And when we rotate around the x-axis, this space right here will be empty. And it'll be empty right down here as well as you rotate. So what we have then is a washer. And with the washer, we're going to have what's called an inner radius, which would be here, and an outer radius, which would be here. I'm not sure how to spell outer. I think it's just one T, and if that's incorrect, I am sorry. So in order to figure out exactly what's left, if I take that outer radius, and we'll call it big R, and subtract it from my inner radius, we'll call it little r, that'll give me this shaded in region. But also, it's a circular area. So we want that outer radius squared and the inner radius squared. And we're going to multiply it by pi. And that will get me the area of the region we're interested in. So if I need to find the volume of this, then what I need to do is integrate my area equation. Remember, volume is equal to the integral of the area. And in this case, my area is going to be r squared minus r squared times pi. Why? Because if I find the outer area, that would be pi times r squared. And if I find the inner area right here, that would be pi times r squared. Well, how do I find out the area left? I subtract those two. So all I've done is factor out the pi. Okay? So set your integral up. We're going to do our top function minus our bottom function. We're going to go from 0 to pi over 14. Of the top function, in this case our big R, so that's the y equals 1, so 1 squared, minus the smaller function, the inner function. Let me see, let me clean this up just a little bit. 1 squared minus the square root of sine 7x squared times pi times dx. Okay? And you can punch this into your calculator. This actually works out halfway decently because when you square root, you're just going to be left with the sine of 7x, which is a very easy use substitution. If you're one of my kids, you can punch this into your calculator. That will help as well. When it's all said and done, if you do it by hand, you should end up with an exact answer of pi squared over 14 minus pi over 7. If you do it on your calculator, you should end up with 0.2562. And that would be units cubed. And I don't know if I put that on the last one, but we are talking about a volume. So anytime we talk about volume, we're talking about things being cubed. So there you go. This would be a washer, using a washer method. And again, anytime you rotate around an axis, you're going to get a circle, and it doesn't matter what it is, because you're looking at one specific point that moves and rotates. The dx accounts for an infinite number of those points, and that's why this equation can work when you're looking at volumes. All right, the last example we're going to look at is a shell method, and shell method can be a little bit tricky, but it can come in very handy as well, and it's just like a washer. There are times when you want to use it and times when you don't. So if I tell you use the shell method to find the volume of the shape created by y equals 2x cubed, y equals 2x, and for all the x's greater than or equal to 0. Here's what we've got. Graph this so that you have a good look at what's happening. And when you graph it, you're going to have a cubic equation, which is going to come this way, and that way? Well, again, we're only interested in what's going on the top. So this is 2x cubed. And the line y equals 2x. That's bad. That's bad. Let me give us a better look. There we go. And both of these go through the origin, even though my blue line doesn't quite make it. So the next thing that we want to know is, at what 2 points do these guys intersect? Okay, and they intersect at the point 0, 0. And they intersect at the other point. Gosh, I don't know. Well, you can set them equal to each other. So 2x cubed equals 2x. Divide both sides by, subtract 2x from both sides. Factor out a 2x. And then set each piece equal to 0. So 2x equals 0 and x squared minus 1 equals 0. So when x is either equal to 0 or when x is plus or minus 1, these graphs will connect. So obviously my picture is very poor because I don't have that third intersection point. But needless to say, I do know though that we're going to rotate around the y-axis and we're going to use a shell method, okay? And when you try to find the volume of an area based on shell, we're looking at this area right in here, okay? When you try and look for that volume based on shell, if you rotate around the y-axis, you're going to use x equations, okay? Y equals equations. If you rotate around the x-axis, use x equals equations. And so when you find a shell, you're going to integrate, let me get a color we can all see, from A to B on the y-axis. So because we're integrating, we're going to integrate from here to here on the x-axis, okay? So that's going to be from 0 to 1. And when we do this, we're going to integrate 2 pi times the radius times the height. Okay, and radius and height can be tricky, but remember, we're creating a shape that goes around the y-axis. And so the height then, if we use a shell, our height is actually up and down. Okay, so this represents the height of the shell, top minus bottom. So when we're integrating this, we're looking at the height would be the top equation minus the bottom equation, or 2x minus 2x cubed. And the radius is just how wide is the shell, like what value are we going to? So our radius is actually going to be wherever we stop moving away from that point of rotation. Well, if we move along the x-axis, it's going to be x units. So in this case, our radius is x. If we move along the y-axis, our radius will be y. So what we're going to integrate then is the equation from 0 to 1 of 2 pi times x times 2x minus 2x cubed. And I am not very good at drawing in 3D, or I'd give this guy to you, but basically what we're looking at is, again, take that Pringles can and imagine the Pringles can as a shell, but now this time it's up and down this direction. So how wide is the Pringles can? It's x units from the center of the Pringles can. That's the x value, all right? How tall is it? Well, the height is the top equation minus the bottom equation. That's the height of the Pringles can. And so when you integrate with shell, that's how you need to think. And if you Google calculus shell method, there are excellent pictures that show you what a shell would look like, and that might help you as well. My kids, you can punch this into your calculator. Other kids, you may need to go ahead and solve this out by hand. Either way, I'll give you both answers. You should end up with 8 over 15 pi if you go by hand. If you use your calculator, you should end up with 1.676, and both of these would be units cubed because we're talking about a volume. All right. Also, a lot of something to keep in mind is sometimes it's easier to integrate and find a volume with a washer than it is a shell. There are also times it's easier to integrate and find a volume with a shell than a washer. And those equations are just a little bit different, so you have to pay attention to that. This one's not too bad. So there you go. That's how to find the volume of a function using a shell method.